In this video, we're going to go over some basics of circular motion. So we'll be coming back to this topic a few times over the course of the quarter, refining it, giving a little bit more detail about circular motion. So in this section, we're going to talk about uniform circular motion. So the uniform means uniform speed, uniform circular motion. So this means constant speed. So whatever's moving around in a circle, it's going at constant speed. Okay, last time we talked about the general motion r as a function of time. There was some x piece that depends on time and some y piece that depends on time. So what your textbook does is it says, well, let's look at a particular case of x of t and y of t, and that is plugging in r cosine. Now, I would plug in theta right here, but because an object is moving in a circle, theta is going to change over time, and the simplest case where the angle is going to change over time is that it's proportional to time. Right, so you're gaining an equal amount of angle every second, for example. That's one way of seeing that this is that the object is moving at a constant speed. It's really a constant angular speed, constant speed and constant radius as well. So the object isn't allowed to change its radius either. Constant speed, constant radius. Okay, so r cosine omega t in the I hat direction and r sine omega t in the j hat direction. So I might not put parentheses around here sometimes. It's understood that the omega and the t have to be in parentheses. One way to see that is whenever you take, so whatever appears inside the cosine or inside the sine has to have no units. So if you have time here by itself, or this other thing by itself, which has units of 1/seconds, that wouldn't make sense. It doesn't make sense to take cosine of some number of seconds. You have to take cosine of a dimensionless quantity. So omega is, this thing omega, it's a Greek letter. This is called angular speed. Or angular, it's called a few things. Angular speed or angular frequency. Sometimes it'll even just be called frequency. We got to be a little careful because we're going to have another variable here called f, and that's also called frequency. So I'm going to try to avoid as much as possible just saying the word frequency. I'm always going to modify it to specify whether we're talking about this thing omega or the thing f. Omega is a measure of how quickly the thing is spinning around, right? If omega is huge, then a small time will do a big change in angle. So it sort of makes sense just based on what we wrote down so far, that the bigger omega is, the faster this thing is spinning, omega. And we can actually show that this is true by finding the velocity. So just to make this look nicer, I'm going to switch colors right now then. The velocity is the derivative of r with respect to time. And remember, in a Cartesian coordinate system, this is easy. You just take the derivative of each piece separately. So this involves using the chain rule. So r is a constant. We're going to take the derivative of cosine, which is minus sine. So it's going to be minus r sine omega t, but then because of the chain rule, we also have to take the derivative of the inside with respect to time, which is omega. So this is r omega minus r omega sine omega t I hat plus r omega cosine omega t j hat. And you can see the magnitude of this thing, the speed, if we do square root of vx squared and square root of vy squared. Using the fact that sine squared plus cosine squared is 1, you can show that this is just omega times r. Okay, so this is one key result for uniform circular motion. So anything that's moving around in a circle, something's moving around in a circle, the radius isn't changing and it's moving at constant speed. This is the speed. And the speed is always in the tangential direction. Right? So this is the speed of that object, and it's in a direction tangent to the circle. If it wasn't tangent to the circle, then the radius would be changing. Okay. So one way to show that it's tangent to the circle is to take your velocity vector and take the dot product with the position vector. So if this is r and this is v, one way to show that v is tangent to the circle is to show that the dot product is 0. Or in other words, the angle between those two vectors is 90 degrees. So if you take that vector and you dot it with r vector, you should be able to show that that it's 0. So you get a minus cosine sine plus cosine sine equals 0. Okay. Okay. So now the next step is to solve for the acceleration. Acceleration is the derivative of velocity. So we're going to get another factor of omega from the chain rule. So this is going to be minus r omega squared cosine omega t, and then minus r omega squared sine omega t in the j hat direction. And the key thing to realize is that if you look at this right here, if you look at r as a function of time, so that's r cosine plus r sine. This is minus r cosine minus r sine. So this is, other than if you factor out a minus and an omega squared, this is the same thing as r of t. Okay, so this is saying that, so r is from the center of the circle to the point wherever the particle's at. The acceleration is always towards the center of the circle. So it's saying that the acceleration is towards the center of the circle. Another thing that we can see right away from this is what the magnitude of that acceleration is. So the magnitude of A is omega squared times the magnitude of r. And the magnitude of r is the radius of the circle. So we call this acceleration the centripetal acceleration. So centripetal means center seeking. So this name sort of makes sense now. It's always being, in order for a particle to move in uniform circular motion, something needs to be pushing it. So we haven't really talked about forces yet, but you can believe that an acceleration is because something is pushing it in that direction. So hopefully that's not too big of a leap. So in other words, this particle wants to keep moving in this direction, right? If there was nothing pushing it one way or the other, it would keep moving along that direction. Something is always causing this particle to turn left, right? And so turning left means, like, so in whatever direction the particle is headed, left would be towards the center of the circle. So at this point right here, left is towards the center of the circle. When the particle is going down right here, so from the perspective of the particle, if something's pushing to the left, something's pushing towards the center of the circle. Now the acceleration does not have a component in the direction of the velocity or opposite the velocity, which is why the particle doesn't speed up or slow down. So the acceleration is non-zero, and the acceleration is changing the direction of the velocity, but not the magnitude, because the two are perpendicular. Okay. So this is centripetal acceleration. AC. So the magnitude is r omega squared, and then if we take this and instead write it in terms of v instead of omega, we have v squared over r. So you might see that equation for the magnitude, or if you also want to keep track of the direction, you might see centripetal acceleration is v squared over r, and then maybe a minus r hat. Remember, r hat is a unit vector pointing outward from the center of the circle, so minus r hat is pointing inwards. And this is just a unit vector, so it's not changing the magnitude. So writing it this way makes it clear separately what the magnitude and the direction are of the acceleration vector. So acceleration is towards the center of the circle. Another way of saying that is it's radially inwards. Okay. Okay, so I mentioned omega is a speed. It's saying how fast the particle is moving around the circle. I want to mention a couple things about that. So maybe more info about omega. So I skipped over this part in the book, but omega, so your book introduces another thing right here, this capital T. So this is the time, so omega is going to be a constant. The bigger omega is, the faster the thing is moving around a circle. So given omega, you can also introduce this thing called capital T, which is the amount of time it takes for the particle to go all the way around the circle. And all the way around the circle is 2 pi radians. It's 360 degrees or 2 pi radians. So omega is 2 pi over the period. So this t is how long it takes for the object to move around the circle. So capital T is the letter we almost exclusively use for period. And it's how much time to complete one revolution. Yeah. One revolution around the circle. And then t is 1 over the frequency, 2 pi f. So once you know one of these three things, you know the other two. So omega, t, and f. That was unintentional, the order. Once you know one of those three things, you know all three. So omega is the angular frequency. The units are radians per second. So if omega is 2 pi, for example, that's saying that the particle is undergoing 2 pi radians every second. So if omega is 2 pi, it takes just 1 second to go around the circle. If omega is 4 pi, then that means the particle is going around twice in 1 second. It undergoes 2 circles in 1 second, 4 pi radians per second. So omega is how much angular spread, angular displacement the particle undergoes in 1 second. So radians per second, or you might see it just as 1 over seconds. So a radian isn't really a measure of it doesn't have units. It's not like meters or seconds or kilograms or anything like that. So I want to point out one other small thing. Angular. So if you have a section of a circle, you have some arc length, and you have a radius and you have an angle, then the arc length is equal to r times theta. This equation is true as long as theta is in radians. So theta has to be in radians. And this is exactly why we use radians instead of degrees. It's so that we could use this formula right here. And then notice how if you take a derivative of both sides with respect to time, you get the speed, which is how quickly the arc length is changed, how quickly you're gaining distance along the arc. So ds dt is v is r is a constant, and then derivative of theta with respect to time is this thing omega. Okay, so this is like what we mentioned before with v equals r omega, but in a little bit more detail. And this is also saying why we need to choose radians. Okay, we already talked about t, period. This f is called natural frequency. Or sometimes just frequency. So I guess I guess it depends on who you talk to, but if you just say the word frequency, in a lower division course, normally we would just say F. In a graduate course, if you just say frequency, we're probably referring to omega. Omega turns out to be more useful, but what you're probably more useful is F. What you're more used to is F. So natural frequency, you might see it as 1/seconds, but that's bad because it really is confusing with this. So I'm going to try to avoid 1/seconds. I'll really just try and write radians per second for omega. And then for natural frequency, this is in cycles per second. It's how many times you go around the circle in 1 second. So if f is 1 per second, 1 cycle per second, that means the particle undergoes 1 circle, 1 revolution per second. So cycles per second is another word for this, or another unit for this is hertz, Hz. Hertz means cycles per second. You never call this one hertz. This is bad. We never use the word hertz for omega. If someone says something has a frequency of 3 hertz, they don't have to use the word natural frequency. They can just say frequency because it's implied when they say the word hertz that they're talking about natural frequency. Okay. And then from the equation, you should see that if f is 1, if you're going around one circle per second, that's a radian. That's an angular frequency of 2 pi radians per second. So the equation should make sense at this point. And then f is 1/t. So it makes sense that so if period is period is seconds per cycle. How much time to complete 1 revolution? Seconds per cycle, or seconds per revolution, or just seconds? So seconds per cycle, if you take the inverse of that, that's cycles per second. So it makes sense that these two are related just by one is the reciprocal of the other. Okay, I think that's all I want to say about frequency and period at this time. But we're going to be using all 3 of these terms quite often in this course. Okay, we're in a position to answer this now. A bug is standing at the edge of a turntable. It will slip if the centripetal acceleration required for uniform circular motion is greater than 0.4 g. What is the minimum period the turntable could have so that the bug doesn't slip? So our formula, so we're given a condition on the centripetal acceleration in this problem. And we're asked something about the period. So the chain of like equations here that we can use, we're given info about AC. So it looks like, that's equal to v squared over r. It's also equal to r omega squared in the negative r hat direction. So given AC and the radius, which we're also given in this problem, right? The radius is 0.25 meters. So we have a condition on A, we have the radius, we can solve for omega. And then once we have omega, we can relate it to the period using this. Okay. So I think we're in a position to do this problem, right? So the original problem. So AC, so I'll prove, I want you to not be so scared of inequalities. So I'm gonna slightly complicate this so it's not just algebra that we're doing. So I'm going to say that the bug doesn't slip. The bug doesn't slip as long as the centripetal acceleration is less than or equal to 0.4 g. Okay, this is what the problem is saying. It's saying that if this is the maximum value it could have any lower value, right? 0.2 G would be fine. The bug wouldn't slip. Okay, so this is the maximum value, so it doesn't slip. And then AC is the thing that we can set equal to R omega squared. Right, so let's go ahead and do that. So AC is R omega squared. It's less than or equal to 0.4 G. And then for omega, we can plug in 2 pi over T. 2 pi over T squared is less than or equal to 0.4 G. And the problem is asking about period. All right, so we want to solve for T. And when I say solve for, we have to be a little bit careful because this is an inequality rather than an equal sign. Right, so it's not too bad though. Right, so we have 2 pi squared times R over T squared is less than or equal to 0.4 G. We can take the reciprocal of both sides, so T squared over 2 pi squared R. But if we do that, then we have to switch the sign of the inequality. Right? If like 1/4 is less than 1/2, that's true. If we flip both sides, we have 4 and 2. So all of a sudden, this needs to go in the opposite direction. Right? So if you take the reciprocal of both sides, you have to flip the sign of an inequality. So this is greater than or equal to, and so this is gonna ruin our significant figures. But maybe just to help with writing this algebraically, I'm gonna write this as 2G over 5 instead of 0.4. I'm gonna call it 2/5. So I'm gonna kind of pretend it's exact and then do my rounding at the end of the problem. Okay, so we need to take the reciprocal of the right-hand side, which is 5 over 2G. So then we can multiply both sides by 2 pi squared R. So T squared is greater than or equal to, so let's see, the 2 squared divided by 2, looks like this is 10 pi squared R over G. Does that look okay? I think that's okay. And then taking the square root of both sides, we get square root, I'll just put everything inside the square root, 10 pi squared R over G. So remember what the inequality is representing. It's saying that the bug doesn't slip as long as this is true. So this is bug doesn't slip if this is true. So the period has to be big in order for the bug to not slip. We can keep decreasing the period, capital T. So that means speeding up the turntable, right? Speeding up the turntable will decrease the amount of time it takes to undergo one revolution. We can keep speeding it up until the period has, the lowest possible value it can have is this. So we can see a little bit more clearly why this is a minimum value, right? So you can kind of get away with ignoring this word and just setting all these things equal and just finding the some critical value. But this is nice because it really shows that this is a minimum. So T min is equal to square root of 10 pi squared. Let's see, the radius was 0.25 meters. Then divided by 9.8 meters per second squared. So the minimum frequency is, I apologize I didn't do this in advance. 10 pi squared, 0.25. Remember, I already took into account the 0.4 G because that's built into the 10 pi squared and everything else. Looks like this is 1.6 seconds. Okay, so plugging in the numbers, we get 1.6 seconds. But I also like, we want to get you in the habit of solving things algebraically first and then plugging in numbers at the end. Okay, I think that's it.